All right, so we're ready to start into the last chapter for the class, chapter 11 on analytic geometry. And we're going to do just three sections in this chapter, and then we'll finish out the course. So objective one, we want to be able to graph an ellipse centered at the origin. And before I do that, I just want to review just a couple of things. One is, in this chapter, we're going to look at four types of curves called conic sections in this chapter. And actually, the first one, a circle, we you would have looked at in college algebra. So we're going to look at these cases, the ellipse, hyperbola, and the parabola, right? And I just want to point out a couple of things. So this green looking shape, this is technically called a double napped cone. And what you can see is this like brownish piece of paper looking thing. This is a plane, right? So it's a like an infinite sheet of paper, if you will. It's a two-dimensional sheet of paper. And what we're going to look at essentially is the intersection of a plane and the double napped cone, right? So hence, this is where the term conics comes from, right? So it deals with a cone, so that's where we get the word conics from, right? So in 11.1, we'll look at ellipse, and then the future sections, we'll look at hyperbola and parabolas, right? So just to review really quick, right? You should already know the standard form of a circle, right? So if a circle is centered at the point HK with a radius r, then we get the equation x minus h quantity squared plus y minus k quantity squared equals r squared, right? So like here's an example of the equation, and we can see the center and radius, and there's a graph pretty easy, right? So that should all be review, right? So then, the one that's at least the most related to a circle of the conics is an ellipse, so it makes sense to, cover that next. So an ellipse is kind of like a squish circle, if you will, right? So an ellipse is a set of all points, x, y, in a plane, such that the sum of the distances between x, comma, y and two fixed points is a constant. The fixed points are called foci, plural focus of the ellipse. Right, so I have a couple of diagrams here. So this first one is when the major axis is horizontal, and the second picture is where the major axis is vertical, right? It's on the y-axis. So the major axis is the longer axis, right? So you can see like here, this is much longer than the this green one here, right? So forth. So the major axis is the longer of the two. The foci are going to be points, fixed points on the major axis, and the vertex is also going to be on the major axis, right? So those are like the endpoints of the major axis, if you will. All right, so you can see that information. So what I would like to do now is I found this animation to show you, just to kind of make more sense of this definition of what an ellipse is. So this animation, so you can think about, we have this blue and red line, so I don't think I can pause this, right? But the thing to get from this is as the points move around, what you want to notice is the blue line plus the red line remain constant, right? So the entire time in this diagram, no matter where the point xy is on the ellipse, the blue line plus the red line is a constant 10, right? So that stays at a constant value, right, for that specific ellipse, right? So that was, part of, the main definition of an ellipse, right? That's what this is meaning, is the sum of the distances between x, y, and two fixed points is a constant, right? So in other words, if I get rid of this, if this, let me try to zoom in on this a little bit. Like if this is my point x comma y, right? Then the distance from the foci to that point remain constant. So we could let this maybe be d1. Oops, let me make this a little finer. Oops. This could be like d1, and this is d2. So in other words, d1 plus d2 is going to be some constant value, right? And you can actually go through and kind of use this information in this diagram and construct the equation of an ellipse from this by giving some points of labels. So if you look in this section in the textbook, it actually goes through part of that proof. And I actually decided to not do that proof formally just for time's sake. I don't know that it's super important since this class isn't like a proof-based course. So you actually see on page 2, this is the diagram to kind of start that process, to be able to derive the formula of an ellipse and where that comes from. But I won't go through that formula. That will take quite a bit of time, I think. So you can look over that in the textbook if you'd like. So we're going to actually skip over page 2, and I would like to jump to page 3, which this has an important table that we're going to use a lot in this section, right? So you want to print out this table and have it by your side when you're working through a lot of these equations and so forth. So what we have here is the standard forms of an equation of an ellipse centered at the origin are as follows. Assume that A is greater than B, which is greater than 0, right? So notice that A and B are both positive, right, the entire time in this chart. And then the length of the major axis is 2A, and the length of the minor axis is 2B, right? So that's all going to be the case throughout, right? So remember, A is the bigger value, right? So whatever number the bigger value is under, right? So like here, there's A, and here there's A. So what this tells me is that my major axis is on the variable that's above the bigger number, right? Same thing here. So notice how that goes hand in hand, right? So if the a squared, the bigger value is underneath x, then the major axis is along the x-axis. That's the longer side, right? The longer part of the ellipse. And then the major axis on the y happens when the bigger value, which is a, is underneath the y squared, right? So that's how we can tell in general. Another thing I want to point out is notice how in order for it to be the equation to be in this format, it has to be equal to 1, right? So that's going to play an important role for us as well, right? And then both cases here, the center is at the origin, and actually there's a objective in the class to look at when the ellipse is not centered at the origin. But we're actually that's actually omitted from Math 1149 at Ohio State, so we won't be looking at that. We're just going to keep it centered at the origin, and then remember the foci, right, are these fixed points here, right? So there's a foci, there's foci, and then these points would be the foci, right? Those are found by using the C value. Right? And it's important to note this equation, right? How you find C is you have to use that equation to solve for C. Right? And then we can find these endpoints for the major and minor axis. And remember, the endpoints on the major axis, we call those vertices. Right? There'd be these points here. Right? And then the endpoints on the minor axis would be these points. Right? Good. So you definitely want to become comfortable with this chart, and we're going to use that information a lot. right? So let's look at an example. So example 1 and 2 are similar. They just have slightly different graphs. So one has the major axis on the x-axis, and the other has the major axis on the y-axis. So what we're asked to do is graph the ellipse, identify the center, vertices, minor axis, endpoints, and foci. So we want to be able to graph both of these, and I provided both graphs for those questions, right? So if you wanted to generate those, probably the best website to use would be Desmos. Desmos, you could get a, type that equation in exactly, and it would give you a good graph for that, right? So the first thing when I'm looking at this graph that you want to notice is that this 9 is the bigger value, right? So what that tells me is that my ellipse is going to be going this way, right? Side where the major axis is, on the x-axis, right? Because it's underneath the x squared. So that's important to note. So that, and remember, a is going to be the bigger value, right? So a squared is going to be 9, and b squared is going to be 4, right? So if I take the square root of those, we would get a equals 3, and b equals 2, right? And of course, typically, when you're solving a squared equals 9, you would have a equals plus minus the square root of 9, which would be plus minus 3. But remember, we said that a is bigger than b, which is bigger than 0. So we're assuming that a and b are positive the entire time, right? That's why I didn't write that in this context, right? So I won't mention that every time, but just note that when I'm solving those, I'm just going to write the positive value down, right? All right. So the center, supposed to identify the center, which that of course is 0, 0, right? Because we're only going to deal with that in this class, centered at the origin, and that value is of course here. Right, there's the center, and then the vertices, right, can be found by the points a, comma 0, and negative a, comma 0. Right, so just filling in the a is 3, just filling that in, we get the points 3, 0, and negative 3, 0. So that's these points here, right? So then, and I'm pulling this information from that table, right, on the previous page. So then the minor axis endpoints, this is the next thing we want to find. That'd be 0, comma b, and 0, comma negative b. Right? So b was equal to 2, right? So this would be the point 0, 2. And 0, negative 2, right? So that would be this point and this point, right? So in other words, this is my major axis, right? And that's called the minor, right? So just to practice those terms. And then the last thing we want to find are the foci, which are this point and this point, right? These are the foci. So the foci is c, comma 0 and negative c, comma 0, where c squared equals a squared minus b squared, right? So c squared is equal to, so a squared was 9 and b squared is 4. So 9 minus 4 is 5, right? So that tells me that c squared equals 5. So c would be equal to radical 5, right? And again, a, b, and c we're assuming are positive, so we just write the positive root, right? So that would be the coordinates square root of 5, comma 0, and negative radical 5, comma 0. Right, so that's what these 2 points are. They're not at 2, they're actually at radical 5, 0, and negative radical 5, 0. Right, so not too terribly difficult. So this next one, the equation, remember we want it equal to 1, right? So here this was nice because this one was already solved for 1, but they're not always going to be like that, right? So looking at this equation, I want this to be equal to 1 in order to get it in that standard form of an ellipse from our table. So an easy thing I can do here is just divide both sides by 900. Right, so that would of course give me 25x squared over 900 plus 9y squared over 900 equals 1. So then 25x squared over 900, I can simplify that to be x squared over 36. And then 9y squared over 100 can be simplified to be y squared over 100. And that's equal to 1. Right? So a red flag that should be pointing out is that's the bigger number, right, between 100 and 36. So that tells me that my major axis is along the y-axis, right? So my ellipse is going to be looking like this, right? Like looking taller instead of, wider. So we assign a squared to be that bigger number and b squared to be the smaller number. So that tells me that a is 10 and b is 6. Okay. So we're going to need to know that information. So then the center is at the point 0, 0, of course, right? The vertices are 0, a, and 0, negative a, right? So just filling in our value for a, which is 10, that would be the point 0, 10, and 0, negative 10, right? So then the next thing we're asked to find are the minor axis endpoints. So that would be at the points b, 0 and negative b, 0. So b was 6, so this would be at the point 6, 0. Oops. And negative 6, 0. Right, so the next thing we're asked to find are the foci. So that's at 0, c and 0, negative c. So we have c squared equals a squared minus b squared. We have this equation to help solve for c. So c squared is equal to, that would be 100 minus 36, which is equal to 64. So that tells me c would be the square root of 64, which is 8. Right? So that would be at the point 0, 8 and 0, negative 8. Right, so we found all those points, and we can see that the dots here for those points are all in the graph, right? So you can just look at those and notice, here are the foci, there's a center, these are the vertices, and then we have these points here, which are the minor axis endpoints, right? So then, as I mentioned, objective 2 is omitted from the class. So let's jump to objective 3, which is looking at using ellipses in some applications. So example 3, what we have is a tunnel has vertical sides of 7 feet with a semi-elliptical top. The width of the tunnel is 10 feet, and the height at the top is 10 feet. Right, so if we try to draw this a little bit, it's like maybe here's the ground, and here's the tunnel, and it has a semi-elliptical top, so something like that. Right, so semi-elliptical is like half an elliptical, right? Just like a semicircle is, like half a circle, right? So then, what we're told is it has a vertical sides of 7 feet, so like here to here, is 7 feet. The width of the tunnel is 10 feet, right? So from here to here is 10 feet. And then the height to the very top is 10 feet, right? So in other words, this part is 3 feet, right? So part A, what we're asked to do is write an equation of the semi-ellipse. For convenience, place the coordinate system with 0, 0 at the center of the ellipse, right? So the center of the ellipse would be, here where this red dot is. So we're going to let, this be my x-axis and this be my y-axis, right, to be able to draw this. So if I kind of just pick that apart, and I'll just draw this here, just kind of like blow that up, if you will. Then here's what we have. We have this picture, right? So from this picture, right, I can come up with these points pretty easy. So, the width is 10 feet. So if the center's at 0, 0, then this point would be the point 5, 0, right? And this point would be negative 5, 0, right? And then this part of the, that I put a blue line in the top here, that's 3 feet. So that tells me that this ordered pair would be 0, 3, right? So in other words, the length of my major axis would be 10, and the length of my minor axis would be 6, right? So that's just 5 and 3 doubled, right? So, because typically, we'd have our ellipse, it would, keep coming down here with the gray, right? So then here is a length of 6, and here is a length of 10 feet. So that's how we know, remember the major axis is always the longer axis, right? So what we can gather from this is, this would be 0, b in the form, so b is equal to 3, and then these points like 5, 0 and negative 5, 0, those would be in the form negative a, 0 and a, 0. So in other words, that tells me a has to be equal to 5, right? So now I can start to build this equation, right? We could have x squared over a squared plus y squared over b squared equals 1, right? That's the generic formula. So then if I plug my values in for a and b, we get x squared over 5 squared plus y squared over 3 squared equals 1. And in this case, we should say that y has to be greater than or equal to 0, right? Because notice, this dashed gray part, that would be when y is less than 0, and that's cut off from the graph, right? That's not part of the graph. So this would give me x squared over 25 plus y squared over 9 equals 1, and this is y greater than or equal to 0, right? So this would be the equation of that ellipse, right? And actually, since y is greater than 0, what you could do is you could solve this equation for y, and when you take the square root of both sides, you wouldn't have a plus or minus because we're assuming y is 0. So you could, this turns out to be y equals 3 times the square root of 1 minus x squared over 25, right? So this is just an alternate form of that equation. And that's not a cubic root. This is 3 times the square root, right? So the index here is actually 2, right? So just to make that clear. Right, but this, first equation in the box is perfectly fine, right? So then to construct the tunnel, so part B, to construct the tunnel, an engineer needs to find the location of the foci. How far from the center are their foci, right? So remember, the foci are at the coordinates 0, c, 0 and negative c, 0, right? So what we're missing is the value for c. So remember, c squared equals a squared minus b squared. So a squared is equal to 25 and b squared is 9, right? Just pulling it from our equation, right? So then this would equal 16. So c would be equal to the square root of 16, which is equal to 4. Right? So these points would be at 4, 0 and negative 4, 0, right? The foci, right? So like here and here roughly, right, are the foci. So to answer the question, we would say that the foci are 4 feet from the center, right? So we got that question answered. And then another application, example 4, we have that Charles and Bernice, which he goes by Ray, were American designers who made major contributions to modern architecture and furniture design. So I'm supposing those are famous designers, right? So suppose that a manufacturer wants to make so maybe Eames elliptical coffee table, which is 90 inches long and 30 inches wide, out of an 8-foot by 4-foot piece of birch plywood. If the center of a piece of plywood is positioned at 0, 0, determine the distance from the center at which the foci should be located to draw the ellipse. Right. So one thing kind of the applications that we've been looking at so far is using an elliptical shape, in some kind of architecture, like building something, right? So that's a pretty common use of ellipses. So we can start to kind of draw this, right? So basically what we have is we have this elliptical shaped table, and this length is 90 inches, and this length is 30 inches, right? And it doesn't really matter if you draw it, sideways or up and down ellipse, because it's just a table. We can move it around, right? So I just for ease, I have a preference. I like it when the major axis is horizontal along the x-axis, so I just drew it like that, right? So what we want to do is actually make where this is the x-axis and this is the y-axis, right? So that way the center is at the origin, right? So then what we could get, just thinking about this a little bit geometrically, we could get this point to be 0, 15, right? Because it's 30 inches total, and so we'd have to divide by 2, right? So then this point would be 0, negative 15. And then we have to divide 90 by 2 to get 45. So these points would be 45, 0 and negative 45, 0, right? So then, from the table, these generically are 0, negative b, and this is 0, b, and this is a, 0 and negative a, 0, right? So by recognizing that, you should be able to get that a is equal to 45 and b is equal to 15, right? So filling that in, we have x squared over a squared, which is 5 squared, plus y squared over b squared, which is 15 squared, is going to equal 1. So the equation, just simplifying that, would be x squared over 2025 plus y squared over 225 is equal to 1. Right? So that's not the answer, but I'll just put a box around that because that's my equation. Right? Remember, what we're trying to find is the distance from the center for the foci, right? To be able to draw the ellipse, right? So we want to be able to draw this ellipse, the shape that they want on the piece of plywood. Right? So to do this, let me change colors. The foci are at the points c, 0 and negative c, 0. Right? So we want to find c. So remember, c squared is equal to a squared minus b squared, which would be 2025 minus 225, which is equal to 1800. Right? So that turns out to be c equals, so if we simplify this, you take the square root of 1800. This simplifies to be the square root of 2 times 900. So 900 is a perfect square, which is 30. So this would be 30 times radical 2, right? So c equals 30 radical 2, which is approximately 42.43 inches. Right? So that's the solution, is that the distance from the center for the foci should be drawn, about 42.5 inches, right? Right. So then, the last objective in this section is looking at another type of application. And this comes up a little bit with an application with how planets have an elliptical path that they follow, around the sun. So to be able to discuss this, we introduce a new term called eccentricity. So the degree of elongation of an ellipse is measured by the eccentricity E of the ellipse, right? So then this table, we have the equations, right? But what we can actually do, since we're not discussing anything, about the center of, HK, we're doing everything about the origin, you can actually ignore these parts, right? Just be x squared over a squared plus so forth. So when we have it in that form, the eccentricity is just the value c divided by a, right? So the same equations we were doing before, we just need to identify the c value and the a value and then divide those, and we can come up with that, right? And the eccentricity of an ellipse is a number between 0 and 1, right? So e is always in between 0 and 1. So then, with this definition, we can see that the eccentricity of an ellipse is the ratio of the distance between a foci and the center of the distance between a vertex and the center. That is E equals C divided by A, right? So then what I have here, I'll show you next, is I want to show you this animation here that's actually in the textbook, in the ebook. So let me just...
An ellipse is shown along with the two foci of the ellipse. Move either focus to the right or left to see the effect on the eccentricity of the ellipse.
All right. So right now where the foci are, we have an eccentricity of 0.8. So it's kind of interesting, if I move these. So if I move these where the foci are on the, the major, in other words, the vertices of the ellipse, notice the eccentricity is a 1, right? So it makes like a straight line. And then as these foci go closer and closer to the center, it looks more and more like a circle, right? And actually when they're both at the origin, right, they're both, over top of each other, we get a perfect circle, and the eccentricity is 0, right? So that's kind of interesting, right? So in other words, the closer that the value is to 0, the more elongated it is, notice. But then, or excuse me, I said that incorrectly. The closer it is to 1, right? The closer the eccentricity is closer to 1, not 0, 1, it looks more elongated. And then the closer that the eccentricity gets to 0, the more circular the shape looks. Right? So that's interesting to note. So then here's just a couple of diagrams, talking about the eccentricity. So there's a couple examples. So you can take a look at those, right? Just some examples. And then now we have to start looking at application. So the orbits of the planets in our solar system are elliptical with the sun at one focus, right? So the eccentricities given in the table below, this information, is from NASA. Right, so you can see various planets, and note that Pluto is labeled as a dwarf planet, right? And then there's some other terms here. So it says the point in a planet's orbit where it is closest to the sun is called a perihelion, and the point where it is furthest away is called aphelion. Right. So have an example to practice this, example 5. So knowing those terms will help us being able to draw the diagram correctly. So it says Pluto is 7.376 times 10 to the 9th kilometers at aphelion, which is a reminder the furthest point from the sun. Use the eccentricity of Pluto's orbit of 0.2488 to find the closest distance between Pluto and the sun. Right. So essentially, we have this elliptical path that Pluto's going to follow, right? I'm just going to draw in, my major, draw my x-axis, which is the major axis, right? And then, here would be like the center. Maybe here would be the sun. And then, this point is going to be the point where we have the perihelion, right? That's going to be the closest point that that Pluto is to the sun, and then way over here is going to be the furthest point away, right? Remember, that's called the aphelion, right? So then, thinking about this diagram a little bit, the distance between the center and this vertex over here, that has a distance of a, right? And then the distance between the center and the sun has a distance of c, right? So this is just from that table and being comfortable with what those a and c values mean, right? And then, so in other words, this distance between the furthest point away from the sun and the sun would be a distance of a plus c. And then the shortest distance then would actually be a minus c. Right, so it's important just to kind of fill that in so we can look at this. Right, so then we can just make some notes that we have two unknowns. So we need two equations that tie this stuff together. Right, so one thing I can fill in is I know the distance of the aphelion, right? That's this part here that's given. So in other words, a plus c, right, just from the diagram, is going to be equal to 7.376 times 10 to the 9th kilometers, right? And that's in scientific notation, right? So that's one equation. Another equation, we'll call this equation 2, that we can get is using the eccentricity, right? So this is found by taking c divided by a, which is equal to the eccentricity, which is 0.2488. And then so what I would do is multiply both sides times a to get c equals 0.2488 times a, right, to get maybe a better form of that equation 2, right? So, basically we have a system of equations that we want to solve, which is a plus c equals 7.376 times 10 to the 9th, and c equals 0.2488a. Right, so I'll call that equation 1, that equation 2. So I think the easiest thing to do would be to solve this by using substitution. Right. So I can just take this value for c and plug it in here into equation 1. So we would get a plus 0.2488 times a equals 7.376 times 10 to the 9th. So this gets me 1.02, that would just be 1.2488a equals 7.376 times 10 to the 9th. And then if we want to get a by itself, we would divide both sides by 1.2488. Right? So this ends up giving me a equals 5.906470211 times 10 to the 9th. And this would be, in kilometers. Right? So we have this value. But we also need to find c. So c is equal to 0.2488 times a, which would be equal to 0.2488 times 5.906470211 times 10 to the 9th. And this comes out to be 1.469529.789 times 10 to the 9th. So the closest distance, which is what we're after, and in the diagram, that's this part, right? So that would be equal to a minus c. Whoops. Change back to a pen here. A minus c. So if I take, take A, this value, minus C, this value, what you should get is 4.4369 40422 times 10 to the ninth, which is approximately 4.437 times 10 to the ninth kilometers. Right? So that's the answer that we're after, right? So you can see how we're using, we're applying ellipticals to this situation. Right? So you can see that, studying elliptical curves would be important to astronomers, right, as an example. So then examples 6 and 7 are not so much applications, but just, using eccentricity a little bit with elliptical equations. So example 6, we're given an equation of an ellipse and asked to find the exact eccentricity. So remember that the eccentricity is equal to C divided by A, right? So what I want is I need to find the values for C and A. So in order to do this, I need to put this equation in that standard form, right? So in other words, I'd want to divide both sides by 12. So that gives me 3x squared over 12 plus 4y squared over 12 equals 1. And simplifying this, we get x squared over 4 plus y squared over 3 equals 1. Right? So in other words, the bigger number is going to be a squared, and the smaller number is b squared. Right? So a is equal to 2, and b would be equal to radical 3. Right? So then c squared is equal to a squared minus b squared, which would be equal to 4 minus 3, which equals 1. So c would be the square root of 1, which would just be positive 1. Right? So since I know c and I know a, I can just fill that in so that e equals c divided by a would be equal to 1 divided by 2, which is 1/2. Right? So that's what we were after. Right? So not crazy difficult. Right? And then the very last one, we're given the center, the eccentricity, and the length of the major axis that's vertical, and we're trying to use this information to find the equation. Right? So an important part to get started here is that the major axis is vertical. Right? So what that tells me is my picture is going to look like this, right? Where this is the x-axis and this is the y-axis. So, this here is my major axis, which has a length of 82 units, right? So what that tells me, this length of 82 units, that tells me that A must be equal to half that, which is 41, right? 41 units. So the eccentricity is equal to 40 divided by 41, which equals, remember, taking C divided by A, right? So since we already know A is 41, then this is going to give me that C must equal 40, right? Because that's the numerator. Now it's important though, like if A was actually like 82, then we'd have to solve this like a proportion, right? But in other words, you're multiplying by 1 on the top and bottom, right? Like in your proportion. So that makes that part a lot simpler. So then, C squared, what we're missing is what the B value is. So we need to use this equation in order to solve for B. So this would give me, so I want to solve for B. So essentially, I'm subtracting C squared from both sides and adding B squared to both sides to get B squared equals A squared minus C squared, right? So this gives me that B squared equals 41 squared minus 40 squared, right? Which this turns out to be 81. So that gives me that B would equal the square root of 81, which is 9, right? So I know that A is 41, B is 9, and C is 40. Right, so those are kind of like all the parts that we need to be able to find whatever we want about the equation or the ellipse. So the equation standard form is x squared over b squared plus y squared over a squared equals 1, right? And notice I put the a under y because this the major axis is going vertically. So that would give me x squared over b squared, so 9 squared, which is 81. And then this would be y squared over, and then we would take, 41 squared, which is 1,681, and that's equal to 1, right? So that, in the green box, is the equation of the ellipse that we're after, right? All right, so that's all I have for that section, so make sure you let me know if you have any questions. Thanks.